Everyone, in this video I'm going to talk about how to find the inverse Laplace transform of a function using counter integration. Now the formula of the inverse Laplace transform is given by 1 over j2 pi integration from sigma minus j infinity to sigma plus j infinity for f of s e to st ds. Now the reason why this function is not very well known, I know that 99% of engineers have never heard of this formula. Actually, it's very difficult to evaluate this integral. It involves non-elementary functions, high-order functions. Okay, you can't even evaluate this integral, even if f of s is the simplest function, just like 1 over s. Even in this case, you can't find this integral. It involves exponential integral, which is a non-elementary function. So engineers find the inverse Laplace transform just by using inspection. Here we will use this formula, but with a trick of the counter integration as follows. So if this is S-plane, okay, and we have a function, f of s, that have a region of convergence, real part of s larger than 1, for example. Okay, so here's the region of convergence of this function. Now, the inverse Laplace transform includes integration from sigma minus j infinity to sigma plus j infinity, where sigma is a constant number that lies within the region of convergence. So let's just take sigma equals 2. Okay, so we have to integrate from 2 minus j infinity to 2 plus j infinity to evaluate this integration. The trick of counter integration is to add a new path to integration to make an enclosure by adding this semicircle. Okay, so we will write that f of s, f of t, equals to 1 over j2 pi integration over this path, which we will call c, for example, f of s e to st ds. Now, the reason why adding this new path will not affect the value of the integration can be illustrated as follows. Let's just call this straight path, okay, c1, and this semicircle path, let's just call it c2. There are parts of the whole path which called c. So we can write the integration in two parts. We have integration with path c equals to integration over path c1 plus integration over path c2. Now the integration over path c1 is the same as the inverse Laplace transform given by this formula. While the addition of the second path c2 of a semicircle will not add anything to this value since it gives you 0. Why this happens? Because the large circle over here, this circle have a radius that approaches infinity. Now if you substitute such values of s into right here, then you are not going to get anything, because e to st, for very small values of s, I mean negative values, s approaches minus infinity, plus minus j infinity, you will get 0. So the result of this integration is 0. It always happens regardless of the value of this function f of s, since e to st is a very strong decaying function. The idea is, if we could convert the integration into a closed contour integration, then we can use the Cauchy integral formula, where the closed integral for f of z divided by z minus z naught dz is g2 pi times f of z naught. Okay, let's take examples. How to evaluate the inverse Laplace transform of 1 over s. Okay, this function have a region of convergence as follows. Real part of s is larger than 0. Here we plot the S-plane. Okay, now the region of convergence is right here, the right hand side, where sigma is larger than 0. We choose sigma equal 2, and we should integrate from 2 minus j infinity to 2 plus j infinity to evaluate the inverse Laplace transform. Now, how should we do the enclosure? Should we do it this way or this way? We'll see about that. Let's do it this way. Okay, now when f of s e to st ds, when we go in this path, okay, s values will be such as plus minus j infinity minus infinity, since we are closing it in the left hand side. This is plus j infinity, this is minus j infinity, this radius of this circle is very large. Okay, this is very good news, since e to st, when s equals such a value, will give you a very small number, and walking in this path will not add any result to the integration result, which results from this path. Okay, but what about the value of t? Now, if t is a negative number, there will be a multiplication by a negative number over here with this s. we get plus infinity, we get plus sigma. And there will be a disaster since you get infinity and you change the result of integration by adding this path. So this is not acceptable. Okay, let's divide the problem into two parts. Part 1 where we assume that t is less than 0, t is negative. Okay, now we have earlier experienced that adding this path to integration path will be useless since e to st will produce a very large number and would change the result of integration. Okay, what about this path? It is true that s will take very large positive numbers in this path, okay, such as infinity plus minus j infinity, okay. Now the important part that will provide decay into e to st is the real part. The imaginary part just provides sinusoidal, which will provide decay or expansion is the real part, which is infinity over here. But we have assumed that t is less than 0. This means that e to st will be e to infinity plus minus j infinity, which are the values of s in this path, but multiplied by a negative number, such as negative 5, okay, when t equals minus 5. So there will be a minus infinity as the real part of s times t. So in the end, we get minus infinity plus minus j infinity. The result is 0. So adding this path will not affect the result of integration, which depends on this path. Okay, so the result of integration from 2 minus j infinity to 2 plus j infinity for 1 over s e to st ds. We converted this integral 1 over j2 pi into 1 over j2 pi integration over this path, okay, for 1 over s e to st ds. Now, since we have no poles inside this enclosure, inside this contour, it's just an analytic function. F of s e to st multiplied by 1 over s is an analytic function. So the result of this integration will be 0. Now, this is true for any value of t that is less than 0. Okay, now we assume that t is any number that is larger than 0. Now, in this case, we can't make an enclosure to the right-hand side, since t is positive and s will take positive values, real positive values. This will cause divergence to the integrand. So we will enclose it this way. Okay, now, while t is positive number, but s will take negative numbers, so the result is e to st will have a very large negative number, minus infinity plus minus j infinity, and will provide divergence to the integration. Actually, this path will never add any value to the result, since it's always 0. So 0 plus 0 plus 0 plus 0, all over this path will add nothing. Okay, so we have converted the integration of 1 over j2 pi from 2 minus j infinity to 2 plus j infinity for 1 over s e to st ds, while t is larger than 0, into this integration 1 over j2 pi closed integral over this path for 1 over s e to st ds. Okay, now we have a pole right here, and we have it really enclosed it. So the result of this integration, according to Cauchy integral formula, will be 1, since we are substituting 0 at e to st. Now, e to st corresponds to f of z in Cauchy integral formula, and 1 over s corresponds to z minus 0 in the Cauchy integral formula. So we should substitute z naught equals 0 in f of z, which is e to st. So e to 0 is 1. Okay, to summarize this, we say that 1 over j2 pi integration from sigma minus j infinity to sigma plus j infinity, we chose sigma as 2, for example. Any value of sigma that's larger than 0 is useful. ds equals to 0 if t is less than 0, and 1 if t is larger than 0, which is defined as the unit step function. Okay, the last example is what's the inverse Laplace transform of e to 1 minus s over 1 minus s. Now, the region of convergence for this function is the real part of s is less than 1. So we have f of t equals to 1 over j2 pi integration from sigma minus j infinity to sigma plus j infinity for e to 1 minus s over 1 minus s e to st ds. I will rewrite it as follows: 1 over j2 pi integration from sigma minus j infinity to sigma plus j infinity for e2 plus 1 times e2 minus 1 plus t by s times s ds over 1 minus s. Okay, now we have a critical value here when 1 minus 1 plus t will be larger than 0 and when it will be less than 0. Now if t is less than 1, we get minus 1 plus t less than 0, a negative number. And to obtain convergence, we need a very large positive number to obtain convergence. So we would like to enclose a circle on right hand side in this case. I assume that we use any value of sigma that lies within the region of convergence, which is real part of s less than 1. Say we used sigma equals minus 5. Okay, don't forget that we have a pole at s equals plus 1. Okay, so we have enclosed this pole in this case. So the result of integration will be e to 1 times e to minus 1 plus t times s when s equals plus 1, which is the value of this pole. So we get e to 1 times e to minus 1 plus 1 plus t, multiplied by 1, and this gets to e2 plus t. This is only true if t is less than 1. Now if t is larger than 1, then this value, minus 1 plus t, will be a positive number. What we will need is a very large negative number, which is s, to satisfy convergence. Okay, so we will enclose the circle like this on the left hand side to obtain that very large negative s. Okay, we earlier said that sigma equals minus 5 over here. Now the pole was at s equals plus 1, so there is no any poles in the circle, so the result of integration will be 0 if t is larger than 1. So we can say the inverse Laplace transform of that function will be e to t times 0 of minus t plus 1.